Got it? All right, let's begin with a word of prayer. Dear Heavenly Father, we thank you for today. Again, Lord, I thank you for these students. Thank you for jury duty being canceled so we can have class again. Pray be with us today. Help us to glorify you, Lord, and we do. In your name I pray, Lord Jesus. Amen. All right, so examples of surface integrals. All right, so I just want to, what I'm trying to do here is just take a few minutes with each one of our standard examples and just try to exhibit a little bit more on how the flux is calculated, how to understand it, try to gain a little bit more intuition for what's going on here. First of all, the sphere, right? So if you look at a little patch on the sphere, the ds there would be what? If you look at it, you can see that if you sweep, if this here is the d phi, what's the radius that you're sweeping out from the origin along as phi changes? It's the whole spherical radius, right? So the little arc length in corresponding to the subtension of d phi. What I'm trying to say is we can write this as the change in the phi direction times the little change in the theta direction, all right? So the change in the phi direction is really just nothing more than rho d phi, all right? On the other hand, if I make this picture bigger, so let's see here. I don't know if I can draw this worth anything. This right here is corresponding to the d theta. It's just not quite the right picture. How to draw this? Maybe. I'm trying, guys. I always have trouble with this particular picture. So this is like the little change in theta. What's the radius that's being swept out? It's from the z-axis, right? It's r. What's r equal to? Rho sine phi, right? So the little distance along that direction is rho sine phi d theta. And so there you go. That's why the scalar surface area element for the sphere is something like rho squared sine phi d theta. Now we derived that by calculating the magnitude of the normal vector field for the usual parametrization of the sphere yesterday. I just wanted to show you can derive it geometrically like this, although maybe it's not convincing given the poor quality of my pictures. I don't know. Now, of course, the surface area element, the vector surface area element, ds, is then rho squared sine phi d theta in the rho hat direction. All right, so that basically gives us the roadmap for how to geometrically calculate surface integrals. Let's look at some examples. Find flux of, let's say, f equals to z hat through sphere radius r, just the upper half. Upper hemisphere to be more descriptive, all right? So here's a picture of what we're doing. There's the sphere of radius r, half of it, the hemisphere, right? I'm assuming that the orientation of the sphere is upward, the positive orientation, it's outward. And if I was to draw this, the vector field F is very boring. It's just this thing, right? I mean, it's always everywhere on this silly thing. It's just, constant upward z-hat vector field. What do you guys think the flux would be? Yeah. Yeah. The heart of what you're saying is it would be the same if I asked what's the flux of this same vector field through this disk, right? All things being considered, the flux through the disk of the same vector field ought to be the same. Geometrically, that seems clear, right? Yeah. Okay, let's calculate it. So the integral, let me give this thing a name. I'll call it h sub r for hemisphere. H sub r double integral of f dot ds vector. The point of this vector area element is to give you a mnemonic, all right? To give you a shorthand for avoiding the full-blown parametric definition. In the same way that using dx, dy, and dz for line integrals and plugging in the functions of time and calculating differentials gives you a way of actually avoiding explicit use of the definition, right? So it's a calculational scheme. It's a mnemonic, but it's a useful one. Okay, so f is just z hat. Integral of f. I can't do anything. Z hat. What's the direction of s hat? Rho hat, right? And then I've got myself, what is rho equals to what here? Rho is equal to r, right? So I can plug that in. I can say, okay, so that's really, r squared sine phi d theta. That goes from 0 to pi. That goes from 0 to 2 pi. All right? And then what? Well, what was rho hat? Remember what rho hat is? Rho hat is cosine theta sine phi, sine theta sine phi, cosine phi. So when I take z hat dot rho hat, what do I get? Yeah, just cosine phi, right? So I've got integral from 0 to pi of sine phi cosine phi d phi. In other words, I have 2 pi r squared, and this is what? 1/2 sine squared phi evaluated from 0 to pi, if I haven't made a mistake. Oh, excuse me. Oh. Are you guys writing things on a piece of paper, or are you thinking? Like, what's it going to be? Can we do both? Somebody here should have called me on this by now. What have I done that's crazy? Yeah, it shouldn't be. I mean, geometrically, it's clear it shouldn't be 0. I agree with that. Yeah. Hmm? No, my integration's fine as it's written. It's a yeah.
Shouldn't the bounds on phi be from something other than?
This is what? This is going from phi equals 0 at the top at the North Pole to phi equals to pi over 2. what I've written is the whole stupid sphere, which would be 0, right? Because the z hat goes into the bottom of the sphere, and it goes out of the top of the sphere. Every field line that goes into the sphere goes out. And then that flux would be 0, because there's a total of positive and negative flux. Now here, that's not the case, because we're only doing the half sphere, which is why I should have a 2 here, here, here. That means this gives you a half, and lo and behold, we get what Mr. Wilcoxon had forecasted, which is pi r squared. Well, he didn't quite say that, but the magnitude of the z hat vector field is 1, so the magnitude of the vector field times the area of the disk gives you the flux, which is just pi r squared here. And yes, it would have been the same if we'd used a disk, right? What would the same example look like if we had used the disk instead of the sphere? Well, I'll more on that later. I want to exhaust this standard example just a little bit more. If I have f equal to anything you like, pretty much. I don't know. Coffee. The function of rho, theta, and phi times theta hat, right? Or if I had g is equal to, what's that? Soda. Oh, soda, okay, fine. Soda as a function of rho, theta, and phi. In the phi hat direction. If I took either one of these and I calculated the surface integral of f or g over any, let's say u, and here where u, some subset of the sphere of radius r, the answer here is what? The answer here is 0. Since what? ds vector is equal to r squared sine phi d phi d theta rho hat, right? And rho hat dot theta hat and rho hat dot phi hat are both 0. We worked that out before. Because the spherical coordinate system is an orthonormal coordinate system. The coordinate lines to it meet at right angles. So let's see here. What do you guys think? How would this example be different? What if we wanted to find the flux? One more example with the sphere, then I'll go on here. Find flux of f equal to, let's say, xyz through the y greater than 0 part of sphere. So to draw a picture, this part of the sphere, right? So what does this vector field look like? I mean, it's spherically radially pointing outward. So let's calculate it. The flux. I need to give this thing a name. I'll call it, I don't know, L. They call it R. R, it's the right half. R. R. F dot ds. So we have integral from 0 to 2 pi, integral from 0 to pi, and then this f. Well, I guess I could be clever or unclever here. What would the clever way to do it be? If you fully embrace the method of non-Cartesian coordinates, then you try to do as much as you can in non-Cartesian coordinates. So I was about to just write down Here, I'll tell you what. I'll do it the dumb way first. Cosine.
Bounds are wrong, right?
Yes, thank you. Yes, good. I didn't get you guys 2 times. Very good. Yeah, we'll fix those bounds in just a second here. So this dot with r squared sine phi rho hat, which was okay, yeah, the bounds. Let's get the bounds right. So this right here is theta equals to 0, right? This back over here is theta equals to pi. Theta sweeping from 0 all the way back to pi. So theta goes from 0 to pi. And, oh, now it's right. Because phi goes full sweep from north pole to south pole. So this is the integral from 0 to pi, the integral from 0 to pi of r cubed sine phi d phi d theta. How do I know that? Let me show you the man behind the curtain there. I mean, so this is what you could do if you didn't have any kind of, if you just followed the rule of what we laid down. I mean, this is the parameterization of the sphere in terms of the spherical angles. But if you look at this really, what is this really? This is really rho hat. In other words, this whole thing is rho hat. And this is rho hat. So I take the dot product, I get rho hat dot rho hat, which is 1. And, I mean, I'm sorry, to be more specific, this is r rho hat. So I get r times r squared, r cubed, sine phi remains, and the rho hat dot rho hat gives me back to 1. And then we integrate, and we get, what we got? Pi r cubed times 2. So 2 pi r cubed. What if I had let the theta sweep all the way around? By the way, if 0 less than or equal to theta less than or equal to 2 pi, that means we get the flux of 4 pi r cubed for this example, right? Because then we just have theta integrated from 0 to 2 pi. Instead of giving us pi, it gives us 2 pi. All right. Let's look at another example, or class of examples, really. Cylinder. Well, I'll tell you what, I'll draw it the other way. So again, if the cylinder has radius r, right, you can easily see that this right here would be r d theta. This right here would be dz. So the ds is r d theta dz, which we worked out from a parameterization last time. The surface area element is r d theta dz r hat, where here r hat was cosine theta, sine theta 0, as we've talked about in previous, when we talked about these non-Cartesian frames before. Okay, so what if you wanted to, say, calculate the flux? I'll do something more interesting this time. F of xyz equal to xy squared x squared z through the half cylinder. The half cylinder with, let's say x greater than 0. So to try to attempt a picture of it, just the half cylinder, right? It would be like, it's a sad picture. Okay, so that's the, and I'm going to assume that the cylinder is oriented coming in the positive x direction, okay? Okay, so how would we calculate the flux of this vector field through that half cylinder? I should give it a name, right? We'll call it Hal. Nobody names their kids Hal anymore. What happened? It is an ugly name. Well, I mean, unless you have it. Let's see here. None of you do. We can say whatever we want about it. Right. Okay, so I guess if we're going to use the standard parametrization as I presented last class, that amounts to this, right? We use theta and z as the parameters, right? And the actual thing is our cosine theta, our sine theta, and most boringly, z. In other words, this is x, this is y, and this is z when you actually work it out, right? So I would have, and what's my parameter range for this example? Oh, I guess I need to tell you the height of the cylinder, huh? Otherwise, it's infinite. That would be harder, given that this function is not vanishing or something as you get further away. Let's suppose that 0 is less than or equal to z is less than or equal to, let's say, L. All right. So I should integrate, say, z from 0 to L. And I should integrate x over an appropriate, theta rather, over an appropriate domain. What would that be? We saw 0 to pi worked good for y greater than 0 in the last example. What's a good range to get x greater than 0? Yeah, negative pi over 2 to pi over 2 is a good choice. If you're a glutton for punishment, you could say, I'm going to do 0 to pi over 2, and then I'm going to do a separate integral of 3 pi over 2 to 2 pi. And you can do that if you want, but don't do that. Okay. So f is what it is, right? X, y squared, which is, what have I done? R cubed. X gives me a cosine. I get cosine theta. I get sine squared theta, comma. See, I felt like these examples are too easy. I was trying to go to something a little bit harder. I may have overshot. X gives me the cosine theta. Y squared gives me sine squared theta. X squared is r squared cosine squared theta, right? And what else here? Z. Oh, okay. I should have put the really awful thing in the third component, given what the ds looks like. What's ds? Well, ds is, well, if you don't mind, I'm going to pull the r and the ds out front. Well, fine, I'll leave it here. R times what? Cosine theta, sine theta, 0. So if I was going to be lazier, I should have put all the evil in the z component, because that would have dot producted to 0. Oh well. Too late. So we just have to do this integral. Integral from 0 to L, integral from minus pi over 2 to pi over 2. And what do we have? We've got ourselves r to the 4th cosine squared theta sine squared theta plus r cubed cosine squared theta sine theta, big parentheses, dz. Now the z thankfully integrates to L, right? So this gives you L r to the fourth integral from minus pi over 2 to pi over 2. What's cosine squared sine squared? That's sine squared of 2 theta divided by 4 plus L r cubed integral from minus pi over 2 to pi over 2 of cosine squared theta d of cosine theta. And again, this is theta over 2 equal to oh, that's not quite true. There's a minus if I do that. So we can make a u equals cosine theta substitution for the second integral, but hey, good news. Cosine pi over 2, cosine minus pi over 2, 0. And the other one, that is 1/2, that's actually 1/8 of 1 minus cosine of 4 theta. And if I plug in pi over 2 to that, what does it give me? 2 pi. Oh, no way. Oh, man. No way. Well, it's not wrong. It's just I think this is 0.
I would agree with that.
Dagnabbit. This over here, when I plug in pi over 2, I get 1 minus cosine 2 pi. 0. Oh, but I have to integrate it. Ah. So I get eighth, and then I get a theta minus cosine of, I think I'm overthinking it here. Underthinking it, rather. Minus pi over 2 to pi over 2. So the cosine terms cancel because they both give you 1. So I get minus 1, then I get minus a minus 1 plus 1. Those cancel. But I get pi over 2 minus pi over 2, I get pi. So in other words, I get pi L r to the fourth over 8. There you go. Sorry, I almost talked myself into that integral being 0, but it ain't the case. Okay, so similar to the spirit of this comment, what could you say is automatically 0 for an integral over a cylinder? If you had something that was going in, for example, the theta hat direction or the z hat direction, those kinds of vector fields, doesn't matter what their coefficients are, if the vector field is just in the theta hat direction or the z hat direction for a cylinder, 0. If you calculate the flux, right? Only the r hat component contributes to the flux is the point. All right, let's try to calculate the flux. X, Y, well, let's say Z squared Z through the cylinder. Well, tired of the cylinder. Let's say through the part of the plane x plus y plus z equals to 1 over 0 less than or equal to x less than or equal to, 0 less than or equal to x less than or equal to 1. Upward oriented. What's that? Z squared. So just to give you a picture of what we're doing, you know, here's the whole plane. Well, that's not the whole plane, but here's a picture of the plane. Right? And so if you envision the z-axis here, here's the y-axis, here's the x-axis. If we look at the part over, so here's the unit square, right? That will go up to here to some part of the plane. And that's what I'm calling the surface. So, and I'm assuming the normal looks like this, all right? We'd like to calculate the flux of this vector field through that little parallelogram. All right? How are we going to do it? Well, this isn't really a standard. I mean, you could go back to the graph thing I did last class, but I think it's just as easy to kind of work from scratch. So let's do that. Parametrization for this sphere is, sphere, listen to me. The plane is what? R of, let's use x and y as parameters. So x, y, what's the z then? Yeah. Would it be smarter to not use these as parameters? What would be a smarter choice of parameter here? Well, I don't know. Here's the thing, is I'm tempted to use z as a parameter because then when I plug in z, it's z, but it comes at a cost, right? Maybe the cost is one I don't want to pay because the cost of using z as a parameter is the cost of losing that wonderful little 0, 1 cross 0, 1 domain for the parameters, right? If I use z as a parameter, the domain for the parametrization would be some kind of screwy parallelogram-y thing on the yz axis. You could envision the parameter space that way if we were to use z and y as parameters. So I'm going to stick with x and y. All right. But that is going to make the evaluation of the vector field at the parametrization more ugly. Okay. So then what's the normal? Partial r, partial x, cross partial r, partial y. You work that out. What do you get? Yeah, 1, 0, minus 1 crossed with 0, 1, minus 1, right? What's that, though? All right, x component minus x component's 1. Cross product, let's see your y component. So that 1. Hey, I wonder what the third one's going to be. 0? Yeah, no. Funny. Is this terribly shocking? The normal to this surface is 1, 1, 1? I don't think it's at all shocking. I think it's actually very natural.
Do you think that's one of the things that's obvious enough you can have looked at your equation and plain and test?
Yeah, and I'd been 50-50, I was right. And up to a scale factor. I mean, the thing is, now that we've done it once, yes, for all other problems that are like this one, you can get away with it, right? But that assumes something. That assumes, I think, that the equation for the plane is written such that the coefficient of x, I don't know, there's a normalization issue here I have to worry about. But now that we've done it, here we go, calculation, the flux of the vector field S through the surface S, all right, is the integral from 0 to 1, integral from 0 to 1. And then I have to calculate what is f. Well, I'm not going to, I'll tell you what, I'll just do it, all right? So what I'm writing here, I'll put in green above. what I'm writing here is f of, r of xy dotted with the normal dx dy. Okay, that's what we're going to put down here. Because remember, last time we worked out that the definition, there's different ways of casting the definition, but the straight definition of the surface integral, remember we worked out it's the ordinary double integral over the parameter space omega of f of the parametrization dotted with the normal vector field, where the normal vector field is defined to be the cross product of the partial velocities, like so, du dv. So, this is the definition, essentially, that we can fall back on when it doesn't fit into some nice geometric plug-and-chug kind of example like I've been doing at the start of today. Okay, so I'm just following the definition, essentially, and then so what is this here? X is equal to x, y is equal to y, but there is no x and y in the formula for f, right? I've just got z. Oh, I have z. So 1 minus x minus y, and then what? 1 minus x minus y quantity squared, and then what? 1 minus x minus y again, right? Take the dot product of that with 1, 1, 1, dx dy.
So pretty much you just add them up.
Yeah. So this is the integral from 0 to 1, integral from 0 to 1 of 2 minus 2x minus 2y, and then I got to square this thing, which is what? Shall I do it out on the side? So it's 1 minus x minus y minus x squared minus xy minus y minus xy plus y squared. Excuse me. Which is 1 minus 2x minus 2y minus 2xy. Oh, yeah, sorry. Shouldn't that be plus x squared? Yeah, that should have been plus x squared. And this should have been a plus xy too, shouldn't it? Yeah. They're all positive? Yeah, that's right. Okay, fixed that. Plus 2xy. Yeah. So plus x squared plus y squared? Let me just take a second to simplify this before I start integrating. What is this? This is 1, 3, so I get 3. How many x's? 2, 4, minus 4x. How many y's? Minus 4y. All right. And then plus 2xy, plus x squared plus y squared. So that's the integral from 0 to 1 of 3 minus 2 minus 4y plus y plus 1/2 plus y squared. Which gives me 1, because x squared integrates to 1/2. Oh, thank you. Very good, thank you. Yeah, I had x integrates to 1/2 over here, which is why I had minus 4 over. So I can do it right over there, but not over there. Okay, so that gives me 1 minus 2 plus 1/2 plus 1/3. I'll get it this time. Plus 1/3. Ha ha ha. 2/3. That's a minus 1. Minus 1/2. Minus 1/2 plus 2/3.
Well, there's minus 4y. Should give you another minus 2.
No, I did 3 minus 2 is 1, which integrates to 1. Yeah. So this. Yeah, okay. Which is what? Like minus 3/6 plus 4/6. The answer is 1/6. I mean, come on, it's obvious, right? I mean, from the start. 1/6. You know, there are variations on this question we can ask, right? Like you could be like, what's the flux of a particular vector field through the part of the plane which is cut off in the positive octant? Right, that's another question you could ask. Let's see what time it is. Oh, time flies when you're having fun, yes. All right. One more example today. Find flux of F equals to, and I'll use one of my favorites, the, let's see here, xyz divided by x squared plus y squared plus z squared to the 3/2, all right? And what I want to know is what's the flux of that through the top face here. What's the flux of this vector field through the top face of this cube? And let's suppose that the cube, you know, we'll keep it simple. That this point here will be 1, 1, 1, for example. This point right here would be minus 1, 1, 1, etc. Find the flux of that vector field through that, right? Now, what makes this interesting and complicated is that the vector field, if you envision it, is pointing straight up here, right? But it points radially outward, so it's pointing like, I can't do it, like this. So, you know, it kind of points, you know, it's, I can't do it very well picture-wise, but I mean, this is the spherically outward pointing vector field, so it's not pointing in a constant direction along the top face of this cube, right? And it's got a variable magnitude too, right? Because how far are you from the origin here? At that point, you're a distance, right? This point right here has rho equals to 1, whereas this point out here has rho equal to square root of 3, I think. Because it's out there, it's at 1, 1, 1. From the origin, that's square root of 3 away. So the magnitude and direction of this vector field vary over this surface, even though it is a rather simple surface. So let's set it up. To calculate the flux of this directly, why would I have to integrate? Give this thing an A mess, all right? So I will use x and y as parameters, right? Use x and y as parameters. What do we got? We've got integral from minus 1 to 1, integral from minus 1 to 1, and then f. So what's z equal to up here? the parametrization of this top face is simply xy is equal to x comma y, and then what's the formula for z on the top face of this cube? It's 1, right? Yeah. So you see, even though it looks kind of scary to start with, ds here is simply, ds vector is simply dx dy z hat. That's the surface area element there. And you could go through the song and dance of calculating partial r, partial x, partial r, partial y, taking their cross product, you get z hat. I mean, but anyway, that's already geometrically clear that z hat is a unit vector field, which points in the upward direction, right? And dx and dy, if you look at a little box, little square right here, right? You've got dx, you got dy. So this little surface area element has dx, dy. That's your ds. Okay. So what is f then? F is x, y, 1 divided by x squared plus y squared plus 1 to the 3/2 power. And then, yeah, okay, so dx, dy. So just do that integral. No? Anyway, the answer is 4 pi over 6. Would you like to know how I know that? It's on my paper. That's funny. It's actually not on my paper, but I mean, that's a great comeback. Yes.
Excellent answer.
That was a very funny answer. Yes, go ahead.
Does it have to do with the geometry of the problem that covers
It does have to do with.
percentage of the...
It does have to do with the geometry problem. It does have to do with the fact that it covers a certain part of space. So, next class, we're going to learn 2 major theorems that are going to help us with the calculation of flux in immeasurable ways. The 2 theorems we're going to learn are Stokes' theorem and the Divergence Theorem, which I will state for you now. Stokes' theorem states that the integral of the curl of a vector field over some surface is equal to the integral, the line integral, of the same vector field over the boundary of the surface. That's actually not the one that's at play here. The divergence theorem states the following. It says the triple integral over some volume, let's say E, of the divergence of a vector field F is equal to the surface integral over the boundary of that volume of it's basically equal to the flux. So it's still hard to explain why I know this, sorry. But it has to do with the divergence theorem. I happen to know that the flux, maybe I proved this last time. We actually, we did this last time. We did do this last time. Last time we proved that I don't need this. I'm sorry, I'm an idiot. I mean, it's good that you're seeing it, but last time we proved that the flux over the whole sphere was 4 pi for that vector field, right? But that vector field has spherical symmetry. So the field lines they spread out in all directions being equal, right? There's this homogeneity, or maybe the word's isotropy. But it's the same in all directions. And
the cube divided by 6.
Exactly. The cube has 6 faces, all of which are equal up to going different directions. So it must be that 1/6 of the flux that goes to the sphere, you could inscribe this cube inside a sphere, right? And every line that goes through the cube has to then go through the sphere. I also have in play the idea that no lines are created or destroyed between the cube and the sphere. That's the case because the divergence of this electric field, is 0. But yeah, 4 pi over 6. Maybe we'll understand that more after a few more classes, but anyway, thanks guys. Tomorrow, Stokes theorem and divergence theorem.